Welcome once again to quantum field theory. We're getting now to the point where we can do practical computations for quantities that we could potentially observe in an experiment. So today's topic will be the S matrix for phi-4 theory and how to calculate an approximation for it for small lambda, for small interactions. Now, what we've had so far is not quite the S matrix. So far we've been looking at these time-ordered green function quantities. And these are all of the form of the time-ordered product of a bunch of field operators at different space-time locations. And we came up with a recipe for how to calculate an approximation for these quantities. And I'll write out the recipe here. And the recipe we came up with in perturbation theory is that these endpoint green functions can be approximated by a sum of all connected diagrams with n external points or n external legs. So this word connected here, that's a consequence of this vacuum bubble cancellation property that we proved in the previous lectures. Now this is not directly connected to an observation or a experiment that you can do involving particles. So quantities that we can observe in experiments are more like scattering cross-sections. You accelerate some particles, you make them collide, and then they explode and the debris of particles flies in all directions, and then you can make empirical counts of how many particles landed where, at what solid angle. So those are the kind of experiments you can do, and that's not directly related to this thing here. So we have to do a little bit more work if we want to connect this quantity to an actual observable quantity in an experiment. But before that, and sort of at the same time as that, we're going to have to also confront some problems with this recipe. I spoke about these problems in the previous lecture. Some of these diagrams are not very well behaved, right? They don't evaluate to a finite number. So we're going to have to, we're going to have to do two things at once in this course. We're going to have to learn and accept that the prescriptions that I tell you here will work after some suitable modifications, and we'll just have to accept that. Because at the level of this course, we're not going to be able to prove that that's correct, because in fact, at this level, we can no longer prove that this thing on the right-hand side here actually has anything to do with the Hamiltonian that we input at the beginning, simply because this perturbation series there has a zero radius of convergence. So you have to accept that that's not yet proven, although I think no one would be surprised if someone came along and proved that the computations you do on the right-hand side actually do match the physics of the Hamiltonian. It's just that at the current time, our mathematical apparatus is not well developed enough to be able to prove that statement. So faced with this sort of situation, you have several options. One, which I haven't emphasized so far, but which is the one we're going to adopt for most of this course, is that you promote the right-hand side to a definition. So everything up to now you can regard as kind of motivation for this thing on the right-hand side, which we'll promote to the status of a definition. And then you check that that definition matches what you measured in an experiment, and then you can make predictions and measure quantities to various levels of accuracy, and it's a triumph as a physical theory. That's one action you can take. Another action which we'll explore in the coming course is to make sense of the right-hand side in terms of Wilson's renormalization group theory, effective field theory, I spoke a little bit about that in the last lecture just to make you feel a little bit more comfortable with the idea that some of these quantities are infinite, but we can make them finite. In fact, those two approaches are not unrelated, and we'll learn much more about that in the next semester. But for now, we're just going to have to accept that this is a calculational tool that's somewhat motivated by the actual mathematical apparatus that we put into this calculational tool. But we're not quite ready to use this in an actual calculation because even simple processes seem to give infinities. So I'll give you an example. Suppose we're interested in a 4-point function. And we're going to use this recipe to compute this 4-point function. A 4-point function like this is extremely useful in determining the S matrix, as we'll see in the coming lecture. So we have 4 external points which we label with the positions x1 through to x4. And then we just got to sum all the diagrams with n external points that are connected. So here's a connected diagram. Not fully connected, just connected. Here's another one. And here's the third one. And that's everything at 0th order. First order, no, 0th order. Then we get to diagrams at 1st order, meaning that there's a vertex appearing somewhere. And here's the first one that you can draw. And then there's even more of these first order diagrams. Here's one there. Here's one there where the loop appears on the top. And there's diagrams where the loop appears at the bottom. There's diagrams where the loop appears on the other leg here. The loop appears over here. So there's a whole bunch of diagrams like this that you have to write down. Dot, 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 dot. And then there's the first kind of interesting diagram, if you like. It's this one here. There's an interaction between these 4 external legs right there. And then many, many, many more diagrams with loops superposed on top of this diagram or connected on top. And then we get to a diagram like this. So today's task is to simply announce that these diagrams, where there's a loop on some propagator like this, that these diagrams play no particular role in computing scattering amplitudes to low orders. So we're going to get rid of diagrams like this. Today's task is to get rid of the orange ones. And the argument we're going to use is very similar to this vacuum bubble cancellation, but it's an argument tuned to the observable of the S matrix. So these we can get rid of, and these were troublesome diagrams, if you recall from the previous lecture. This one evaluates to infinity, this particular diagram here. So if we can get rid of these, then that's great. And so I'm going to argue over today's lecture and the next lecture that indeed you can get rid of these diagrams. There's a reasonable argument that by similar to the vacuum bubble cancellation argument that gets rid of exactly these. So many of these divergent diagrams will be gone by the end of the next 2 lectures. which is a good thing, right? It gives us hope that this tool on the right-hand side is useful for actually calculating predictions to physical quantities. And we'll see that indeed everything works fine up until this diagram here. This one here is the one that really will cause the first problems. And about that diagram, we won't have much to say in this course. So the objective in this course is to get you used to the right-hand side, to argue that it's plausible that this is a tool for calculating predictions for and explanations for physical observable quantities, to be able to calculate these terms in some of this perturbation theory here. But when it comes to higher order terms and dealing with the inevitable infinity that comes in this particular diagram here, we have to defer that discussion more properly to the next course, where we need to talk more in detail about how you actually implement this renormalization approach of Wilson. So today's task is not to deal with this, but rather to deal with these diagrams here and argue that their divergences are not going to play a role in predicting scattering quantities. If at any point your tolerance for these infinities is reached, then always evaluate these diagrams in the presence of a cutoff. I explained how to do that in the last lecture, what a cutoff is. Whenever you have an infinity, it'll typically have the form da 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 da, then some integral so that when you evaluate these diagrams and you encounter a divergence, it typically looks like that integral there. It looks like integrating the propagator to some power L. That's the kind of thing that shows up in evaluating diagrams like this one here. And this is divergent. In fact, I'll just stick, even at this level, it's divergent. Oh, yeah, there's no harm in putting the L in there, I suppose. No, I'll hold back on that. So they typically look like this. Now that's divergent. In fact, it's your exercise for the last exercise for this year to determine the divergence of this integral here. How does it diverge? In what sense is it divergent? So divergences typically look like this. And to cope with this, the recipe is to impose this cutoff, is to say instead of integrating over all momenta, we're going to integrate over momenta up to some lambda, which is far further than any lambda achievable in any observation we've made so far. So you replace all divergent integrals to integrals depending on this arbitrary cutoff lambda. And you integrate over all momenta which are less than this value of lambda. That's the recipe for how to cope with these divergences for the moment. So if you're, as I said, if your tolerance for these divergences, these infinities is reached, and you're no longer happy to write down these diagrams because they evaluate directly to infinity, instead think of them as a recipe for evaluating integrals that depend on a parameter lambda. So you might rightly complain that this lambda isn't physical, it's just some cutoff that we've declared. We can no longer measure quantities with a momentum above this lambda, and then maybe our predictions depend on lambda. So that's the concern you may you justly have with putting in a cutoff, that if you impose this cutoff on all these divergent diagrams here, that the answer suddenly depends on this lambda. And if tomorrow I choose lambda is 10 times the value I chose it today, then wouldn't that mean my predictions depend on lambda? So that's a concern you should legitimately have. But it turns out that you can always compensate for arbitrary choices in lambda with arbitrary choices in coupling constants. So that's how you cope, how you explain to yourself how this lambda does not appear in any physical quantity that actually can be observed. But that's more properly belongs to the subject of, as I said, renormalization theory. That full explanation takes a little while, and I don't want to go through it in this lecture, because I'd rather introduce you as soon as possible to quantum electrodynamics. So that requires that we talk about fermions, and so we have the decision: do we talk about renormalization and scalar particles, or do we talk about fermions and photons? And it will make a lot more sense in the long run to do it that way, as I'll argue later. Okay, so before I continue, I just want to check. Yeah. Yeah, that's what I wanted to check. Sorry. Good. All right, the S matrix. So in the previous course on advanced quantum theory, we discussed scattering theory at length in the second half of the course. So I refer you to those lectures for a reminder of what I'm telling you here. And what we learned is that in the typical scattering experiment, you have a bunch of particles in some well-collimated beam, so that they're confined to a thin cylinder at some specific momenta Ka. So you have one bunch of particles flying in some well-collimated beam. You have another bunch of particles flying in the opposite direction, usually also in a well-collimated cylindrical beam at some specific momenta. These particles come in, and at large times in the past, so when the past time is minus infinity, these particles are well separated and well described by the non-interacting theory. And then for a short intermediate time around time is 0, there's a scattering event where these two beams of particles collide, and then there is debris flying off in various directions. And then at late times, very late times, as t approaches infinity, these particles are assumed to be so well separated that again you can approximate the states of this system with the states of the non-interacting theory. So that's the setup of scattering theory. We have two limits: the limit where t goes to minus infinity and the limit where t is infinity. And what we learned in the previous course was that scattering theory is an effective theory for the limits t is bigger than a constant. So scattering theory is a way of just focusing on observable quantities that are well defined at large times. And part of the course, part of our previous course, was to in fact set this equation up. So as I said, I refer you to the previous course in order to see the motivation for this quantity. So this is the quantity that determines whether two particles in some given momenta will collide and fall apart into, say, a collection of n different beams of particles with momenta p1 through to pn. So the actual probability that that occurs, that event occurs, is determined by this equation here. And our task is thus to calculate that quantity here. And we can do that. We're almost at the stage where we can do that. So the difference between doing that and doing what we've been doing so far is not so very great, because all that's missing here is really the idea that there are some external particles here. So we're going to put these in today, and then I'm going to give you a calculational recipe for how to approximate these amplitudes here. So this is very, very similar to what we've been considering so far. So far we've been considering vacuum to vacuum processes. Now we're going to consider processes where particles have a given input momenta and a given output momenta. Now, we have a formula for these momentum states here. Certainly in the free theory, we know how to do this. So one of the key assumptions of scattering theory is that the in and out states, the states of the asymptotic past and asymptotic future, are well approximated, or in fact are asymptotic to the states of the free theory. So this is an absolutely crucial assumption without which we can't go anywhere in scattering theory. Actually, to be consistent with the notation I've been using so far, I'll put a 0 here. So that's the vacuum of the free theory. So to remind you, the picture that we have in scattering theory is this caricature here. So this is in center of mass, center of momentum coordinates, center of mass coordinates. So a scattering event in center of mass coordinates looks like a single particle in the presence of a scattering potential, which is indicated by this blob here. And away from the scattering potential when the particles are close, these trajectories that the particles follow get closer and closer to an effective free trajectory. So this interacting trajectory here gets closer and closer to some out state, and this trajectory here gets closer and closer to some in state, which are both free trajectories. They're the trajectories of the system without the scattering potential. And the task in scattering theory is to say how is a given interacting trajectory asymptotic to some psi in, how is that transformed to a given out trajectory asymptotic to some psi out. That's the task of scattering theory, and that corresponds to only asking questions about observables defined for very large times. So you ignore everything that happens for intermediate times. So this process here, the scattering, the amplitude for the scattering to occur, this equation here, we can actually work on this because we now have an expression for this S hat. We know how to expand that in a Taylor series. That was one of the key results from the Dyson series. We don't know what to do with this bit here and this bit here, but we're about to find out. Now there's a couple of trivial contributions to a scattering process. There's the one where no scattering occurs at all, right? There's an amplitude for a particle just to pass straight through the scattering potential and come out the other end. And that's actually the dominant one when interactions are small, so we like to subtract that off. Otherwise we're going to have this sort of dominant order 1 contribution to all our scattering computations. We only care about the stuff that gets scattered, not the stuff that doesn't get scattered. So we're going to define an operator, this T operator that we introduced last semester, exactly to focus on the stuff that tells us a scattering occurred. This identity here says no scattering. And it's also convenient to introduce another quantity called m, which factors out the conservation of momentum. All right. Step one is to say S has got a dominant identity contribution. Nothing happens. Let's focus on T, which tells us that something happened. But we know that a process where something happens conserves momenta. Right, none of this, we proved that in a previous lecture with this intertwining relation. If you have a symmetry of your Hamiltonian, then it'll be a symmetry of the S matrix. So we know that momentum will be conserved. And so that'll give us a spurious extra delta function here in this amplitude. So let's divide that delta function out here to define a quantity which tells us really just how the scattering process takes place. And I think in last semester I used a 2 pi to the 2. Here we're going to normalize things with a 4. So M is the non-trivial stuff that collects the actual scattering process. That's a plus, yes. Yeah. So total momentum in minus total momentum out. Okay, it's worth pointing out that all momenta will be on shell, meaning we're describing physical particles here, so that the P naught component is given by the energy. Now, some work relates this M quantity here to the scattering cross-section, which is something you can observe in an experiment empirically. I'm not going to go through that work because we did that work in the last semester, but I'll summarize the result. The differential cross-section in the center of mass coordinates is determined by this M quantity squared divided by, as it happens, 64 pi squared energy in the center of mass frame. Okay. So that equation there really justifies our focus on M. This tells us the asymptotic empirical distribution of the scattering, the results of the scattering experiment, which are just like particle clicks in detectors in some solid angle omega. So this quantity here is the differential cross-section. But for the purposes of this lecture, you can just simply ignore all this and accept that m is an interesting quantity to calculate, if you don't want to be bothered with going through scattering theory. Now this equation here is the one we're going to focus on now. This is a very intriguing formula because it's very close to what we've been calculating so far, which have been vacuum to vacuum expectation values. So the task now is to compute star as best we can. Because star is directly related by a couple of substitutions to this differential cross-section. So here we go. We're going to have to do some more unjustified approximations. Yep. There's a 64 there, yes. Question was, is there a 64 there? Yep, there is. So yeah, you should always be puzzled in physics when you see a large number in a formula, because usually there's a reason for it. This is a relatively mundane large number. But if you saw a constant in a formula like 1,386, you should ask, where does that number come from? Because that might tell you something about the system. Large numbers are very strange, unnatural things. So they usually hint at some kind of deep physics, but that large number doesn't. All right, so to compute star as best we can is our task. And to do that, we're going to have to take on another article of faith in order to continue in this course. And actually, I am going to dwell on this article of faith a bit because it is problematic. Okay, this is a difficult article of faith, I think. This one is, especially if you have experience with non-relativistic interacting systems. So I want to say a couple of words about what we're actually assuming in this line here. All right, let's look at this assumption in the box and compare it with something that we've already encountered before. So a little while ago when we spoke about vacuum to vacuum expectation values, these green functions, we argued using this Riemann-Lebesgue lemma that the ground state of the free theory is projected onto the ground state of the interacting theory in the large time limit of applying this propagator there. Do you remember that we covered this? Now, I would claim that's reasonably plausible. So I'll explain a little bit why this is a plausible thing and why it takes a bit more courage to believe than this statement here. So this, which we'll call, say, star, is plausible because if the interacting Hamiltonian is adiabatically connected to the Klein-Gordon Hamiltonian, in a sense I'll describe in a second, then there's a real reason to believe that this ground state here is connected to this ground state here. You don't encounter any kind of crazy change in the physics between these two states. So there's a physical argument. It's not a mathematical argument because we've got interactions that are unbounded, so we can't prove anything. But there's a physical argument for why star ought to be okay. And this physical argument comes from non-relativistic many particle quantum mechanics. So suppose you set up this Hamiltonian H depending on this parameter S. So when S is 0, you have the Klein-Gordon Hamiltonian. When S is 1, you have your 5-4 theory Hamiltonian. Now, a lot of experience with many-body quantum systems should allow you to believe that if the Klein-Gordon Hamiltonian has a spectral gap delta, in fact we know what the spectral gap is, it's in fact m, then there must be a set of values S, maybe a small set, where this operator here continues to have a gap. So I'm going to draw a cartoon of the spectrum of this operator here. So spectrum of HS. Here's a picture of it as a function of S. So when S is 0, the spectrum of HS is just the Klein-Gordon spectrum, and there's absolutely continuous spectrum above some gap delta, which is M. And then as you vary S, what happens? You add interactions between all the particles, and the eigenvalues tend to move around, right? And all these eigenvalue branches up here all interact with each other. But it should be the case that the gap doesn't vanish instantly, right? You don't go from having massive particles to instantly massless particles. So I think it's reasonably plausible physically that, at least for some region in here, this gap is non-zero. You can slowly turn the interactions on, and the excitations of your theory don't instantly become massless. If they become massless, then you need to explain why they're massless, like why is it there's some new symmetry appears in the system. We don't think that that'll happen here. We think we know all the symmetries. So it's plausible that there's this really there's this region where the gap of the Hamiltonian is bounded away from 0. And in that setting there, you can argue that indeed this formula should work. You have a gap, right? So if you recall this Riemann-Lebesgue type argument I gave, it just said that the eigenvalues away from the ground state, there's always an eigenvalue. Every eigenvalue of the interacting model is separated away from the ground state energy by a certain amount, therefore oscillates very, very quickly and self-averages so that you get out just this omega state there. So that's the content, roughly speaking, of the argument that I gave, that omega is equal to this infinite time limit of the free ground state. And you can argue to a reasonable level of rigor that for many models, that's equivalent to being adiabatically connected in the sense of there being a gap open all the way along this path here. So that's something that's plausible. I'm not saying I've given you a proof here, I've just given you a plausibility argument. As long as the particles of the interacting theory don't instantly become massless, these two states should be connected. But what we're saying in this box here is far more radical. In the box, we're saying for an argument like this to work, we somehow need that the gaps around every momentum eigenstate are preserved. Let's call it star, star, star. So in order for that equation to hold, we just need that one eigenvalue gap remains open in order that we can apply this averaging argument. But for this equation to be true, we need that at that given momenta here, in the interacting theory, there are no other eigenvalues sort of close by that could get confused up with this one here. And similarly for that momenta there. So this is a much more bold assumption than the one that we made in star star. And if you have any experience with interacting many-particle quantum theory, you'll know that this is much, much less likely to occur in practice. As you turn on interactions, these things form bound states, they do all kinds of crazy stuff. So we're assuming sort of the best of all worlds in writing this formula here. But this is the formula we're going to take as the basis for our computation. Once we've taken that formula as the basis, taken that formula on faith, then we can actually do lots of computations. So this is certainly not going to be true for large interactions. This is only likely to be true for small interactions. So as far as I'm aware, there does not exist a proof that this will work for even many particle non-relativistic quantum theory. There are problems arguing that such a thing would work. So the state of the art mathematically is very far away from this assumption here. But you didn't come to this course for mathematical rigor. You came to this course so that you could compute stuff and compare it with experiments. So if star, what did I call the box? Yeah, triple star, right? Could be justified So if we could justify that boxed formula, then we could do a lot of computation. And so we're adopting this more pragmatic approach where if it's convenient to make an assumption and it checks out with experiment, then we will make the assumption, so we will. And then let's go ahead and calculate. So this would be proportional, and I write here difficult factor because it's difficult. It would be proportional to a quantity that we could use in actual diagram computations. Now, the argument for that is exactly the same as the Dyson series argument we gave when the right and left hand kets were the vacuum for the green function here. So the idea is to go to the interaction picture here. And that's what allows us to write that as this time-ordered integral of the exponential. So the difficult factor of proportionality, it turns out that can be eliminated in exactly the same way as this vacuum bubble cancellation. Okay. There's a piece of notation that I've introduced here that's going to take a lot of explaining. So this will take this lecture and probably part of the next lecture to explain what this criteria of connected and amputated means. So for the moment, we're going to just simply say that this criteria of being connected and amputated is analogous to this connected criteria we came up with after the vacuum bubble cancellation. I'm going to go through some of the steps of how we get to this and what those two words actually mean in this context. So this is So this formula is to be justified but not proved. We're not going to prove it in this course in the sense that we've had to take on an article of faith anyway in order to get to it. And furthermore, even taking on this article of faith and getting to this stage is quite a non-trivial set of steps. So we're not going to do those steps in this course. But I will justify it in terms of some sort of concrete calculations. So these words here, we're going to define them presently, but for the moment they are undefined. So in order to understand this formula over here, to finally explain what this all means, we're going to use the same strategy we use to evaluate these green functions, which is to say we take this operator here and we expand it in smallness of the perturbation parameter in terms of this interaction term. And then we just sum up the terms. So it's just the Taylor series once again. And the first term we're going to encounter, of course, is the order 1 term, right? When you expand out an exponential, you always get an identity. And it's equal to this, right? The order 1 term is when nothing happens. And there it is. We know everything on the left-hand side here for the order 1 term. We know what the expression for a momentum eigenstate is in the free theory with momentum Ka. We know what it is with momentum Kb. We use this formula we had derived previously, and we come up with this expression here for the order 1 contribution. And it's not bad, it's pretty good actually. We have to contract these operators here. They're not in normal order. You notice that these operators are not in normal order, so we have to commute them past each other. We use the commutation relations for the creation and annihilation operators, and we get some delta functions, and we end up with this expression here. So we can do the order 1 term, so that's pretty good. So if you think of the Green's function case, the order 1 term was easy, it was just the number 1. Well, now it's almost as easy, it's a bunch of delta functions. And indeed, those terms there correspond to the identity bit in the scattering operator S. And diagrammatically, we could represent that order 1 term like that. Well, let's come to the order lambda term. That's where things are going to get interesting, of course. Yep.
Shouldn't we make the diagrams in the momentum space because all our calculations are...
That's a good question. Shouldn't we make the diagrams in momentum space? Yeah, we should. To be consistent, we should do exactly that. Yeah, thank you.
So we should make arrows, don't we?
We should also make arrows, yes, to be consistent. You're absolutely right. And the Feynman rule of imposing momentum conservation gives us this delta function between P1 and Ka. So the first order term comes from expanding this exponential, this time-ordered exponential, and keeping the term to order lambda. So that's pretty easy. We know how to expand things to order lambda when we have an exponential. And we come up with this equation here. So the order lambda term is determined by this equation. Now here we begin to see a difference between the Green's function case and this scattering amplitude case. Because in the Green's function case, we always had that was the vacuum and that was the vacuum. But here it's not the vacuum anymore. There's a momentum eigenstate here and a momentum eigenstate here. So there's going to obviously be some differences when we apply Wicks' theorem to evaluate this expression here. So Wicks' theorem says that the time-ordered product of a bunch of operators is equal to the normal ordered product of the bunch of operators plus all contractions. Aha, but here we see a fundamental difference to this green function case. Remember how the all contractions bit was the only bit that really mattered in the Green's function case. Only the fully contracted bits mattered. But that's because if there were any field operators left over, they were in normal order and they would instantly annihilate the vacuum. But now the vacuum no longer stands there, so we must deal with the fact that we have the possibility that these field operators that are in normal order can still annihilate, not annihilate this state here. So there'll be extra contributions here. So we have extra terms we have to deal with. All right, there's a lot of terms we have to worry about here, so let's do an example to get a feeling for what kind of terms will survive in this inner product here. So the simplest possible example we could do would be to look at the positive frequency, that's the bit that contains all the annihilators, remember, operator applied to some momentum eigenstate P in the free picture, in the free theory. So let's just do this example so we get a feeling for what kind of things are going to come out. Well, we have this nice formula for this guy. That's the guy containing the annihilation operators. It looks like this. I've just substituted in the formula we have for the positive frequency field operator in the interaction picture. And then we've got A, K applied to P. That turns out to be quite nice because we know what P is. Of course, we know that P is just a momentum eigenstate, which we've argued to be normalized, and that's according to that formula here. And now we've got an annihilator applied to a creator, and we can use the commutation relations to move AK past AP. We pick up a delta function, and it annihilates the vacuum. So the final answer is easy. So we can substitute this into the integral, and then we'll get the answer. I've missed out a square root. Sorry about that. Have I? Yeah. There you go. So we know how to apply field operators to momentum states like that. The negative frequency term does something different, but we're going to normal order that to the other side. So we're going to include these initial in and out states in these contractions that are taking place over here by defining additional contraction lines. And then we'll have a calculation or recipe to evaluate those terms. Oh no, I don't want to do that. So we're going to define additional or extended contractions. So this symbol here, whenever you see this symbol, a contraction of a field operator against a momentum eigenstate like that, this will just mean e to the minus I p dot x. Sorry, that's not with underlines there. And similarly, that's not with underlines up there. Damn it. Okay. That's a 4 vector, not a 3 vector. Similarly, we can define a contraction with a bra as e to the I p dot x. I just want to put those underlines there all the time. So now And so now there's a kind of extended Wicks theorem to deal with this case where the time ordered product of a bunch of field operators in the presence of some momentum in and out states, if I got some zeros here, is equal to the all possible full contractions, also including these external states P1 through to Pn and K1 through to Km. And I guess to make that clear, I'll put a sum. So it's this calculational trick that allows us to approximate these S-matrix transition amplitudes. But this is only justified up to that huge assumption we made about momentum eigenstates in the free theory being related to momentum eigenstates in the interacting theory, which is another pill you have to swallow, another article of faith you need to take on in order to continue in this course. So coping with this is not easy because you have to either give up on accepting mathematical rigor or give up on making progress. So you have to do one of these two things to continue in this course. And the strategy that we're employing in this course is to expose you to the calculational tools that you can get by taking on these articles of faith, so that later on you have an experience in what the answers look like when we come to actually interpreting them correctly. Okay, with that I'd like to stop today. Thank you very much.